All right, let's dive into one of the most fundamental ideas in all of chemistry, equilibrium. It's kind of like this hidden principle that governs, well, everything, from massive industrial factories to the tiny microscopic processes happening inside your own body.
So, have you ever been in the lab or even just watched a reaction and wondered why it just seems to fizzle out? You mix your stuff together, it reacts for a little bit, and then it just looks like it's over, way before all the reactants are even used up? What is going on there?
Well, here's the secret. They haven't stopped at all. Not even close. What's really happened is they've reached this perfect state of dynamic balance. It's not a standstill, it's more like a busy standstill, where there's just as much action happening going forward as there is going backward.
Okay, so what in the world does this dynamic balancing act actually look like in practice? Let's break it down.
So, dynamic equilibrium is the point where the forward reaction, that's reactants turning into products, is happening at the exact same speed as the reverse reaction. The key word here is speed, or rate. The reactions are both still going, full steam ahead, but because their rates are equal, the overall amounts of everything look completely frozen. Let's paint a picture. Imagine cylinder 1 is full of your reactants, and cylinder 2, your products, is empty. At first, all the water flows one way, from reactants to products. But as the product cylinder fills up, water starts flowing back. After a bit, the water levels in both cylinders stop changing. Not because the flow has stopped, but because the water is moving back and forth at the exact same rate. That right there, that's dynamic equilibrium in action. So this is the big takeaway. Equilibrium is not about inactivity. It's all about balanced activity. You can think of it like a busy bridge during rush hour. You've got the same number of cars entering the city as leaving it every minute. The total number of cars in the city stays the same, right? But the traffic never ever stops. Okay, so reactions reach a balance. We get that. But where exactly is that balance point? Does a reaction mostly favor making products? Or does it kind of prefer to just stick with the original reactants? To figure that out, we actually need a way to measure the balance. And we do that with a simple little number called the equilibrium constant, or Kc. It sounds kind of technical, but all it really is a ratio. You just take the concentrations of the products, multiply them together, and then divide by the concentrations of the reactants. It's basically a snapshot that tells us exactly what the mixture looks like once it's all settled down into its happy equilibrium state. And the size of that Kc value, it's a huge clue. Think of it like a seesaw. If you get a really big Kc number, it means the seesaw is tipped way over, heavily favoring the products. And if you get a tiny little Kc, well, it's tipped the other way, and the reactants are pretty much all that's left at equilibrium. And here are the general rules of thumb to make it easy. If Kc is bigger than 1,000, the reaction basically goes all the way to completion. You've got mostly products. If it's smaller than 1,000th, the reaction barely even starts. And if it's somewhere in that big middle range, you're going to have a nice, significant mix of both reactants and products just hanging out at equilibrium. Now, this is where it gets really powerful. If equilibrium is just a balance, can we tip the scales? Can we actually manipulate a reaction to get more of the product we want? The answer is a huge yes, and it's basically the secret sauce behind a ton of modern industrial chemistry. And this is the rulebook for how to do it, Le Chatelier's principle. Put simply, it just means that if you have a system that's happily at equilibrium and you stress it out, say by changing the concentration, pressure, or temperature, the system will shift to relieve that stress. It's almost like the reaction fights back to try and find its balance again. Let's see how this works with pressure. So if you crank up the pressure, you're basically squeezing all the molecules together. The system hates that, so to relieve the stress, it shifts to the side of the reaction that has fewer moles of gas, the side that takes up less space. In the famous Haber process for making ammonia, you go from 4 moles of gas down to just 2. So high pressure pushes the reaction to the right, making more ammonia. It's a classic industrial trick. Temperature works kind of the same way. The easiest way to think about it is to treat heat as if it's a reactant or a product. For an exothermic reaction, like making ammonia, heat is a product. So if you add more heat by raising the temperature, the system says, whoa, too much product, and shifts to the left to get rid of it. That's actually why the Haber process is run at this weird compromised temperature. It's got to be hot enough to make the reaction go fast, but cool enough to still get a decent amount of product. Now, you might be thinking this is all just for giant chemical plants, but equilibrium is happening all around us and inside of us. So let's connect it to something we've all heard of, acids, bases, and pH. So the most useful way to think about acids and bases is the Bronsted-Lowry definition. It's simple. An acid is a proton donor, and a base is a proton acceptor. And this simple little exchange of a proton, you guessed it, it's a reversible reaction that reaches an equilibrium. And here's a totally wild fact for you. Even a glass of pure water is in a constant state of equilibrium with itself. One water molecule will act as an acid and donate a proton to another water molecule, which acts as a base. This creates a teeny tiny amount of hydronium and hydroxide ions. And that perfect balance point for that specific equilibrium in pure water at room temperature gives us a pH of 7. That's literally where the number 7 comes from. It's the signature of water's own internal balancing act. So anytime you shift that balance of protons, you change the pH. That gastric juice in your stomach? Super acidic, because it has a massive excess of protons. Milk of magnesia is basic, because it has very few. Every single point on the pH scale is really just describing a different equilibrium position. And maintaining this balance is, and I mean this seriously, absolutely critical for life. Your blood, for instance, has to stay at a pH of right around 7.4. If it shifts even a tiny bit, the equilibrium of countless reactions in your body, like how hemoglobin carries oxygen, gets thrown completely out of whack, and the results can be disastrous. So you see, this dynamic balancing act isn't just some abstract concept from a textbook. It's happening inside every single cell of your body, at this very moment, keeping you alive. Which leaves us with one final thought. With all the different things we eat and drink, how does your body manage to maintain that perfect pH balance, day in and day out? The answer lies in something called buffers, which is a whole other fascinating story of equilibrium at work.